All right, this rather unorthodox video is our introduction to exponential functions. My slideshow software is giving me trouble, so we're doing it half on paper and half as this. Anyway, introduction to exponential functions. So let's have a definition. An exponential function is a function that can be written in the form y equals b to the x, where b is a positive number called the base, and that base cannot equal 1, which is a sensible restriction when you think about it, because if you let it be 1, then it's always 1 to the anything will give you 1, and so that'll actually be a constant function. It won't fit in with the rest of our exponential functions. I do want to emphasize that this base has to be a positive number. That b not equal to 1 is not the only restriction on it. It also needs to be positive. So let's look at some examples. Y equals 5 to the x. Y equals 3/4 to the x. So notice that 3/4 may not be the first number you think of, but it's a perfectly good number. It's not equal to 1, and it happens to be less than 1, but that's fine. It's a positive number. And let's look at this one step at a time. So if I have 10 to the negative x, at first that doesn't look like it fits into the pattern, but I can rewrite that as 10 to the negative 1 times x, which is, according to our reading of the review of exponential rules, 10 to the negative 1 to the x. And of course, raising something to the power of the negative 1 is the same as taking the reciprocal of it. So the reciprocal of 10 is 1/10. So 10 to the negative x can be rewritten as 1/10 to the x. So that is an exponential function that meets this definition. And then finally, y equals 3 to the x, not just any number to the x. That one is what we're going to graph on our next so-called slide. So we're going to complete this table and plot some points and graph the function. So I've got 3 to the x. So if I'm going to use 1 as my input, that's going to give me y equals 3 to the 1, which is just 3. Here, this will give me y equals 3 squared, which is 9. I'm not going to write down each of these, but 3 cubed is 27. 3 to the 4th is 3 times 3 is 9, times another 3 is 27, times another 3 is 81. And we're going to get increasingly big numbers if we keep going in that direction. Notice that my x column has changed to a 0, so I want 3 to the 0. Any number to the 0, well, except for 0, which is undefined, but 3 to the 0 in particular is 1. So any non-zero number raised to the 0 will always give you 1. And then we already mentioned how in the reading it mentions that raising something to the negative 1 is the same as taking the exponent, raising it to an exponent of negative 1 is the same as taking the reciprocal of the base. So 3 to the negative 1 is 1/3. 3 to the negative 2 is the reciprocal of 3 squared, so it's 1/9. And 3 to the negative 3 is the reciprocal of 3 cubed, so it is 1/27. So now let's look at the grid that I have here for us to graph these on. Notice that these numbers get really big and also really small. 1/27th is very close to 0. But also 81 is pretty big. So my x and y axes do not have the same scale, which is fine as long as you make it clear. I've made it clear here. I've got these 1, 2, 3, 4, 5, while the y-axis is demarcated in units of 10, so 10, 20, 30, 40, 50. So I'm going to start plotting my points. When x is 1, y is 3, which would be approximately here. When x is 2, y is 9, which would be just under the 10. When x is 3, y is 27, which will be a little bit under the 30. When x is 4, y is 81, which will be just over the 80. And then when x is 0, y is 1. So let's see, that's 10, so 1 is about here. Maybe that might actually be a little high. When x is -1, y is 1/3. When x is -2, y is 1/9. And on a graph this scale, I think the width of my dot is more than the 1/9 unit. A -3, I'm 1/27th. Now I'm drawing that basically on the x-axis because it is so close to 0, but that really is, it's not 0. And in fact, this function is never going to get to 0. Let's sketch in the curve of this function now. It has this in the positive x direction. Notice that the y is going increasingly up. In the negative x direction, it's getting increasingly close to 0. So we can talk about the end behavior of this function. As x approaches positive infinity, y approaches positive infinity. As x approaches negative infinity, y approaches 0. So it does have a horizontal asymptote, but only in one direction. And there is our sketch of the graph. I will be, or you have nicer graphs to look at that are computer generated, but this is a perfectly good sketch of y equals 3 to the x. Now let's do another one. Let's do 1/3 to the x. So if x is 1, 1/3 to the 1 is 1/3. 1/3 squared is 1/9. 1/3 cubed is 1/27th. 1/3 to the 4th is 1/81. 1/3 to the 0 is 1. Now 1/3 to the -1, raising something to an exponent of -1 means you take the reciprocal. The reciprocal of 1/3 is 3. So 1/3 to the -1 is 3. 1/3 to the -2 is 9. And 1/3 to the -3 is 27. So, oh, my pen bled through. So ignore those dots. And I'll change colors if I had one handy, but I don't. So 1/1 when x is 1, y is 1/3. When x is 2, y is 1/9. When x is 3, y is 1/27. Here it's really hard to distinguish that amount when your graph is this scaled from the x-axis. Now, when x is 0, y is 1. When x is -1, y is 3. When x is -2, y is 9. And when x is -3, y is 27. So, this graph is actually closely related. I might as well actually mention that, hey, when x is -4, it's going to be 81. So we have a similar shape. Notice that it is actually very closely related to the previous graph. It's been reflected over the y-axis. But we can also talk about the end behavior. As x goes to positive infinity, this time y is going to go to 0. And as x goes to negative infinity, y is going to positive infinity. So, we have, oops, we have another slide with the basic shapes of exponential functions. So if we've got the graph of y equals b to the x with an arbitrary b, it's going to look like this if b is greater than 1. So remember, b can't be equal to 1, but if it is greater than 1, it's going to have the general shape of the y equals 3 to the x. It may be slightly steeper or slightly less steep, but it will have the same end behavior, whereas x goes to positive infinity, y will go to positive infinity. As x goes to negative infinity, y will go to 0. And if b is less than 1, it's going to have the same general shape as the 1/3 raised to the x function did. Whereas x goes to positive infinity, y goes to 0. And as x goes to negative infinity, y will go to positive infinity. So those are the two classes of exponential functions. Given knowing what the basic shape is, and also knowing those facts about function transformations that we've had, the same old function transformations from forever, you can sketch a pretty decent graph of any exponential function just by knowing so sketch 5 to the x minus 2 plus 3. Well, y equals, let's bring this around here, y equals 5 to the x has this general behavior, that general shape. Now, if I am subtracting 2 from the input, that's a horizontal shift to the left it's a horizontal shift to the right 2 units. I changed my example at the last minute here. So everything is going to get shifted this way. So I'm going to sketch this roughly. Whoops. Roughly like that. So that's my sketch of y equals 5 to the x minus 2. And then finally, I'm going to shift it up 3 units Now, when I do this, I'm going to also shift my horizontal asymptote up. So, just call this 1, 2, 3. And it's going to look roughly like that. Now, you won't be required to draw perfect graphs of transformed exponential functions. However, you should be able to pick one out of a multiple choice lineup based on the function transformations. And then finally, we're going to write a function. We're going to write 3 to the x plus 5 in the form a times b to the x. Sometimes this is going to be a more useful thing. So notice that right now I have it as a single number with addition in my exponent. Now, one of our exponent rules is that if we have b to the m times b to the n, that's equal to b to the m plus n. That should be prerequisite knowledge, but it was reviewed in the reading. So the way that we usually, or the way that you probably have mostly used that rule is starting with something that looks like this side and simplifying it to something that looks like this side. But I can also start with something with addition in the exponent and break it apart into multiplication. So 3 to the x plus 5 is equal to 3 to the x times 3 to the 5. Now 3 to the 5 may not be something that you know off the top of your head. You're free to use a calculator. It is 243 times 3 to the x. And now the only other thing I want to do is, it did ask me to put the number that's not raised to an exponent in front, so I'm going to write this as 243 times 3 to the x. And there we have it. This is going to be more useful in certain situations, which will come up later. And that is our introduction to exponentials and exponential functions.